Before we jump into the discussion for digital logic buses, let's review the bitwise operator for C language. So basically, we have the logic Boolean operator, and we have this bitwise operator. Okay, so logic operator is like you have the bool data type, and then you can do AND OR and inclusive OR and NOT. So when you do NOT, A, it will be logic-wise, it will convert true to false, or false to true. Okay, so that is for logic. And if you have A and B, that's logic-wise, you would do the truth table for two variable. Okay, so basically you will convert 0, 0, 0, 1, 1, 0, 1, 1, and then this one A and B will be 0, 0, 0, 1. Okay, so that's logic operation, and 0 for false, 1 for true. Okay, but here we talk about bitwise operator. What is the bitwise operator? Bitwise operator usually operate on the data. So what we usually will do is we may have an unsigned character. So this unsigned character say X. So X will have AB. So X will have AB. And then you have another one, say Y. It also has the AB. Right? So we perform the, say we have this single AND operator. We will have 0, 0, the bit level operation to be 0, 0, 1 to be 0, 1, 0 to be 0, 1, 1 to be 1. Okay, so whatever data over here, if it is at 0, the data will fall through. Whatever data is 1, I'm sorry, I make a mistake. Whatever data will be 0 in here, and there is a 0 over there, and then the data will be clean. And then whatever data will be there, if you have 1, the data will fall through. So basically, when you have a 0, that's clean. You have a 1, on the other operator, it will be passive. Okay? And then actually this part, if you have the two operator operands, X and Y, you will get the result for AND. Is that okay so far?
Can you explain that second part again? Wait, why do you stop at 4?
What?
Why do you stop at 4?
Okay, the right-hand side, you understand, right?
Yeah, so why do you stop after 4? No.
Okay, this other, the left-hand side, actually, if here, if you have 0 or 1, right? No matter it's 0 or 1, here you got a 0 because this guy is 0. Right?
Yeah, but I thought you carry over a 1 from the right.
No, this one is AND. Bitwise AND.
Oh.
It's not process, it's bitwise AND. So it will be basically this guy AND with this guy. So if this one is 0, no matter what it is, this one you get a 0.
Yeah.
And then if this guy is 1, no matter what is this guy, this X will pass.
What does pass mean?
It will be the same value as the X.
Oh, okay.
So 0 will be 0, 1 will be 1.
Oh, okay.
You know what I'm saying?
Yeah.
So this is in your logic design, basically, if you have a logic gate, right? And here I connect a 0 and my X coming, the output will be 0. So this one is a clear. Right? Is that okay?
Yeah.
That 0 will be a clear operand. So over here I get a 1. I get a 1, and then this X will pass. This one is useless. Totally useless. It's become a data just go through. So basically by doing this, you actually create something called multiplexing. So what is multiplexing? Multiplexing is like, I have an operator, I have X over here. I have an operator, and I have a Y over here, right? And here I connect it to this guy say here, I have a C bit, right? I have a C bit, and then here I have an inverter connected to here. So this guy will be C will control here, here C bar will control here, right? And two of these right here, I have a OR gate. Here I will have an OR gate at the end. Okay, so if my C is 1, so here's 1, here's 0, right? So 0 basically blocking the Y. So Y will get what? Y will just get 0 because it's clean. It's a clean. So whatever Y it is, it won't pass. X will pass. And since this guy is an OR, so X will pass over here. So eventually X got selected. Why? Because OR gate 0 means passing for X. Is that okay? Is that okay so far?
Mm.
So if I clean this red one, and this time I have a C equals 0, then my C equals 0, my C1 equals 1, right? C bar is the bar for Y, for bar for C. So right here, because my X is 0, so here will be clean to 0. My Y side, the C is 1, I will get 1. Get Y, I'm sorry. Y will pass over. So this result will be Y. So basically, this guy is called multiplexer. This design is called multiplexer. Conceptually, let me clean it. Conceptually, this circuit, let me draw again, and then I explain it, okay? Conceptually, I have like X and Y, right? And actually right here, I have a box, and I use a C to select, okay? And then X will pass by 1, Y will pass by 0. So if 1, basically right here, it has a switch. It has a switch. If C equals 1, my X will flow through. C equals 0, my Y will flow through. Right?
Yes.
Is that okay? That's the function for this multiplexer. So basically, the multiplexer design is like I have an AND gate, and then I have an OR gate, right? And here I have my C connected over, right? And my C converted to bar connected to here, right? So my Y is over here, my X is over here, and two connected together. Is that okay?
Mm.
Is that okay? And this is called a multiplexer. And the multiplexer, if you put a bubble over here, it's the same. Two bubbles will cancel out. And this bubble eventually, it will become a design like this. NAND gate, connected to a third NAND gate. Because this guy, inverted input OR gate is equivalent to a NAND gate by the De Morgan rules. Right? So basically, I can use a C with a inverter, and then my Y over here, C over here, X over here. And then this one say G. G will be X if C equals 1. G will be Y if C equals 0. Is that okay? So real implementation in circuit, it will be like this. But logic-wise, it's just 2 AND gate and an OR gate. So usually we just draw 2 AND gate and OR gate, and the logic design is a different story. So usually the multiplexer, we would design something like this. Logic design, we would just write something like this. Okay? So here you have Y, here you have X, right? And then you have C coming over. Right? Is that okay so far? Is that okay so far for the multiplexer?
Yeah.
This is a two-way multiplexer. Now, if our input is four-way, 4-bit, 4D multiplexer, say I have an A, B, C, D, right? And same thing right here, I would need a N gate, an N gate, an N gate, an N gate. And then I order them together. There's a big OR gate, okay? There's a big OR gate coming out. So each one of them come here. So each one is waiting for an enable signal, right? Some enable signal, it has a give a once here, A will pass. Give a 0 there, my A will be bypassed, right? So now my address now over here, my address over here had 2-bit now. Had 2-bit now. So my address here, let's call this address as say E, okay, I'm sorry. E for 2-bit. So basically you have the E0 and E1, say, okay? So basically my E0 and E1 here, I should have the E0, right? And here I can convert it to an inverter, right? So this one is actually E1 bar, E0 bar, E0 bar. Same thing here, I can generate something called E1 and E1 bar using the inverter by E1, right? So I have the 4 signal coming, right? Now, over here, I can actually have a, here I have an AND gate, right, connected together. So for example, for A, I may connect this one called E0 and E1 bar, E0 bar and E1 bar. So here is E0 bar and E1 bar. So basically here when E0, E1 is actually 0, 0, A will be selected. So in B over here, I can select it what? With say E0 and E1 bar. So say 0, 1, I'll select B. 1, 0, 1, it will select C. And then 1, 1, I select D. So that's a 4-way selector. Is that okay? This is a 4-way
So you
multiple.
need to select which gate to go through?
Yeah. So basically, the right-hand side, I keep an AND gate here as a selector. And it actually uses the combination of the address, E1 and E0. Is that okay? Let me rewrite this one. So basically here, I have a big OR, right? And here I have 4 AND gate. Right, so here I have my A, I have my B, I have my C, I have my D, right? And my address is here now. Let me use a E1, E0 format. Okay, that would be easier. And then my E1 and send it to a converter, right? My E0 send into a converter, inverter, right? So here I have a E1, E1 bar, E0, E0 bar, right? And then here I can connect 4 different AND gates. For address decoder. Okay, so for example, this one, the first one for A, I can connect to E0, E1 bar, E0 bar, E1 bar, and I connect this one to here. So this one 0, 0, active when 0, 0, right? When here is 0, 0, right? This one will be 1, 1. E1, E1 bar will be 1, 1, and you will get when E1, E0 is 0, 0, here will be 1. And then I select this A. Is that okay?
Yeah.
So this one is called decoder.
The one on the right?
Yeah, the one on the right is called decoder.
Okay.
Say I have something like a 2-bit 2 to 4 decoder. Right? I have a 2 to 4 decoder. Is that okay? This on the right is called decoder. This one on the right is decoder.
Is that the 2 to 4 one?
There is a 2-bit, 0-bit, and 1.
Okay.
So on the left is actually the multiplexer. So let's look at the decoder now. The decoder actually right here, say I have my X1 and I have my X0, right? And then basically my design for decoder is like my decoder output will be when I have 0, 0, this one will be 1. Otherwise, it will be 0. 0, 1, this one will be 1. 1, 0, this one will be 1. 1, 1, this one will be 1. Right? So for example, if I pick this one 2, so the logic would be S1 and S0 bar. Right? The design for this A2, A1, A0, A3. So A2 will become equal this. So A1 would be equals S1 bar S0. A0 becomes S1 bar S0 bar. A3 would be called equals S1 S0. Is that okay? So this one is a 2 to 4 decoder, right? And then we may have 3 to 8 decoder. 3 to 8 decoder is like, I have the X0, I'm sorry. I may have X2, S1, X0, right? 3-bit coming, right? And then here is like A0, A1, A2, A3, A4, A5, A6, A7, A8. I'm sorry, not A8, up to A7, okay? So what if we pick A4, say? So my A4 would be X2, S1 bar, X0 bar. So it's like 1, 0, 0. I'll select this one.
So this is a 3 to 9 decoder?
3 to 8 decoder.
3 to 8.
This is 2 to the power 3.
What? Oh, you accidentally put 8.
Is that okay?
Yeah.
So if 4-bit coming in now, 4 would to 16. 5-bit would be 32. Right? So say if we have an 8-bit addressing. So if we have an 8-bit addressing, so A7 down to A0, and I say A8-bit address, right? So it will be multiplexed to 2 to the power 8. So it will be 0 to 255, right? So basically, it will be a decoder. My 8-bit, when I have 8-bit, I put it this like this. My address has 8-bit, right? And you will actually provide from 0 to 255 selector, and each one will be A0 to A255. Okay, so let me put this as an input address. Okay, the input address. Okay, so if I say I have something called 00001000, right? This one actually what? A8 will be ignite, or it will be 1. Others will be 0. So I select some of them, some of the bit or bytes from there. So this is actually A to 256 decoder. and that is for addressing, right? That's for addressing. So from my sales side, right? From my sales side, actually, right here, I have a sale. I have my SRAM or DRAM cell over here, right? So right here, this address will connect it to an end, and this one will be selected, right? And then there's a big OR. It will be big OR. So all of the 255 would be put in together to there, right? But this design is not practical. I mean, this design is not practical. What really will be used is not like this. What really will be used will be a tri-state buffer. Tri-state buffer is making more sense. It's like my data here will be my data over here will be going through here, and there is a tri-state buffer, and then this address will be connected to here. So only when this one is 1, data will pass. Otherwise, this one will not be connected. And then right here, I connect it to a bit selector, a bit buffer. So all of the cell will be lined up, and then there's an enabler. If the enabler comes is 1, and the data will go. Otherwise, that bit will be totally be disconnected. So tri-state buffer is a better design right here in order to actually allow the data pass through. The AND/OR design actually, when the memory got bigger, it's actually not practical. Is that okay? And simple tri-state buffer is not difficult to design. Simple tri-state buffer is not difficult to design. It's just a logic gate. So this will be a tri-state buffer. This design will be a tri-state buffer. This one will be a tri-state buffer. Okay. This design is a tri-state buffer. Okay. What it is actually, okay. Let me actually. There are 2 designs for this tri-state buffer. What is tri-state buffer? Tri-state buffer is drawn as this, right? So here is a selector, and your data is over here. So when selector is 0, then D is floating. D out is floating. Output data is floating.
What does it mean by floating?
Floating is not connected. No 0, no high level or low level. So if I have two tri-state buffer, D0 and D1, and there's a select 1 and select 0, right? Say if my S1 is 1, then here I have a bus, right? So there's no current going in or going out if it is tri-static.
So it's dead?
It's totally like disconnect. And then this guy can just drive the data by if S1 is 1.
Oh, okay. So tri-state means it's not.
It's like
it's just
0 or 1 or disconnect.
Okay. Zero just means it's not flowing through, right?
It's actually floating. Just disconnect mode. It is a disconnect mode. So one design is like this. One design is like this. One design is like this. Like this. This is one design. Okay. So right here, I have an inverter over here, right? This is one design. And then here has an inverter. Right? So my data A here should still be A, right? Right? So my selector, if this one selector and this one selector bar. If my selector is 1, selector bar is 1, right? The data here will just go through. So you will get A. Right? If my selector is 0, my selector bar is 1. Right? So basically, this one is off. This one is also off. So there's no current going through or going, no, there's no current. So here it becomes floating. Is that okay?
Yes.
So it effectively is like this. This effectively is like S over here, A over here. Okay, that's one design for tri-state buffer in CMOS.
Uh-huh.
That's one design for tri-state buffer for CMOS. Another one is like this. There's another design like this. I think this one is better design actually. Okay, so here you have an inverter, say, and your S over here. Okay, and your D is over here, your data over here. Okay, something like this. So if my, say now if my S is 1, okay, so here is 1, here is 0 over here, right? So here is what? It actually will be connected. This one will be connected, right? And my data here will be inverted and go through. So here I need to put an inverter in front of it. So inverter, I get my D over here. This one is an inverter, right? Inverter structure. As long as the top power and lower power are closed, connected, it is an inverter. So right here, before I go through right here, I need to put an inverter. I put an inverter over here. Okay, so here I have D, here I have D bar over here. And eventually I got a D over there. Is that okay?
Mm-hmm.
And if my signal now is actually, my S is now actually 0, here we have a 1. So this one disconnected. This one disconnected. Since both of them are disconnected, these two actually either is open or closed. Doesn't matter. So this one basically the D, output D actually is just disconnected from the input. So this one is floating. When S is 0, it's floating. So it is effectively this one the same. It will be the same as this one. The same as tri-state buffer. So tri-state buffer is used in this situation. So tri-state buffer and DMAX both are okay. And small design, you can use the multiplexer. So basically, small design is like you have like A3, A1, A0, right? And here I given the ages of X1, X0. So I will select one model to go through. So 0, 0, 0, 0, this one will go through. 0, 1, this one will go through. Right? 1, 1, this one will go through. Right? That is the max DMAX. And max DMAX have two parts. One part on the right is actually this one for the multiplexer, and the other part is the decoder part. Decoder part on the left. HS bit to control the DMAX, and then your data A and B over here. Is that okay? And this one actually right here, at the bottom part is one. I can replace that by basically by my tri-state buffer. Same result. So this one I connected to A0. This one I connected to A1. A0 equals 1. Is that okay? This design is similar. This design right here is similar to the other design here. The same. Is that okay? Is that okay?
Yes.
So So knowing that electrical capability, actually you should know that there's a logic 0, logic 1, and also maybe a floating state in the CMOS design. Okay. And now we finish the end. That's BY end. And then the next one is BY OR. BY OR.
Same thing.
BY OR is similar but different. Okay, so here, for example, I have, and again, I have a bit. So I have my x0 up to my x7, right? Right, and then I have an OR function now, right? So say here, if I have, I have 0, 0, 0, 1, 1, 0, and then 1, 1. Okay, the result would be 0, 1, 1, 1, right? That's the OR function, right? And here, if I have x, 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 I don't know the state. But here, if I have 0, the x will pass through. It's different from what? Different from NAND gate. NAND gate 0 will clear, and here 1 will set. 1 will set. So 1 it will not pass. 1 it will not pass. It will be set into 1.
Pretty much just following the OR rules, right?
Yeah. But remember, 0 will be passing. 1 will be actually not passing. It will be set. It will be set to some data. So this one, when we have a mask, 1 is using for setting. Okay, if you use OR, and then 0 is used for AND gate to do clear. So that's this one is called set. This one is called clear. Okay. Okay. And passing is actually you use 1 or 0 in AND or is actually different. Okay, is that okay? Is that okay for the OR? So for the OR, I can also use the OR gate to do my selection. So here I have an A, and I have a B over here, right? And at the end right here, I have I have a AND gate, right? So here, if I have this one 0, and then A will fall through, right? A will fall through. And then here, if I have 1 over here, my B will fall through. I'm sorry, this one is 1. Here should be, I'm sorry, here a little bit different. Okay. When I have a 0, I'm sorry. I'm sorry here. Let me clean that. So here, if I have a selector, right? Here I have a selector, and selector equals 0. I put a bar over there, okay? My A will be selected. So when my S equals 0, A will be selected. S equals 1, my B will be selected. And this one is called low active. Remember the previous one used an AND gate. It's high active. High active means high select. Here, when S is low, A will be selected. And S is equal 1, B, S equals 1, B will be selected. Is that okay?
Yeah.
So this is a little bit opposite logic. The previous one is easier, okay? The AND gate is easier to do this. So usually, this one I just show you the concept, but OR gate not used for multiple cell design, usually not, okay? Usually not. Okay, the next one is the BY OR, exclusive OR. BY exclusive OR will be when you have 7-bit, 8-bit. Okay, again, we have 0, 0, 1, 1, 1, 0, 1, 0, right? And then we do inclusive OR. The data will be 0, 1, 1, 0, right? That's following the inclusive OR rule.
Yes.
And here we have S, right? If we have 0, the data will be, the data will be what?
Depends on X.
Depending on X, and then what?
Pass.
If X is 0, what will you get? You will get
0.
0. If it is 1, you get 1.
1.
So this one actually is a fall through.
Yeah.
If it is 1,
then if X is,
you get X bar.
Yeah.
So it's actually, this one is also called toggler. So you have 3 logic, okay? And for clear, or for what? For set. Cap, the inclusive OR for toggler. Toggler means change the data. If it is 1, you toggle. And then OR is like if it is 1, you actually set. And is that you even have 0, you clear. Is that okay? Is that okay? Functional wise, inclusive OR is used for toggling. I don't know what it is. I just want to do toggle. And I set my mask. This one we call it mask. The second operator we call it mask. So say if I have something like if I have said something like x0 to x7, right? My data coming in like this, right? And I don't care. Other operator. I just put a couple of quite many ones, right? I should get x0 bar, x7 bar, right? But actually it's a complement. And in fact, this one is 1's complement. And then you plus 1, you can get 2's complement. Remember that one? Remember that one?
Yes.
So this one actually is BY. This is another one called BY complement. That actually is not. But BY complement, you can use a mask as well. But if you do just like...
So bitwise complement is just flipping
flipping
numbers
bit.
around. Yeah. And then if you add 1, it's
2's complement.
2's complement. Okay.
Yeah. Is that okay?
Yes.
Okay, so right here. Okay, I mimic something called 20 steps, okay? And here, as you can see, I set up quite many different logic functions. Do you see that? I set up quite many logic functions. So for example, the first one, I have Boolean function x and y, right? And I return x and y. So this one actually is the end function.
Huh?
Right? So it basically perform this. Right? Return value. Let's assume that the return value is called z. Right? So this one actually is all the logic gates I have. Right? This is all the logic gate I have. So what is useful for this guy? What is this for useful for this guy? So right here, let me design something called okay, so right here, right here, if I set up this, right? So basically, what I would do is like, I try to simulate this. If I try to simulate this guy, okay, I try to simulate this guy. And right here, what I would need to is what? What I would need is like, here, let me call this one SB, okay? This one we call x1. This one we call x2. This one we call it z. Is that okay? This one in electronic world we call it net. Okay, some point we call it net. So we can program the nets. So here, let me see. I have a Boolean function, a value sp, x1, x2, and z. Okay. Let's assume these are actually sp equals false, s1 equals false initially. Okay. S2 equals 4, that's the initial condition, and G equals false, okay? Okay, and here I have something called integer clock equals 0, okay? And I say for clock equals 1, clock less than equal to steps, clock increase. Okay, and then each time I will do this, my SP equals inverter of S. Is that okay? My S1 equals what? My S1 equals and A and B. No, and A and S. Right? My S2 equals or E and SB. Right? My G equals or S1 and S2. So this is the net discretion. Net discretion, I connected net by using this, right? My SP coming from my inverter function of my S, right? And then my S1 is the output of my end result for A and S, right? My all function for those. Is that okay? Okay. Then each time, let's say I have 3 bit input, right? So here I will say my A equal initial data. A equals clock modular by let's take modular by, let's say no, let me see. Let's say A equals because we want to have its bit. We have 3 bits, so we want to have so we have a clock, right? So clock from 1 to step. So let's assume like no, here let's go 0 to step. Okay, so here let me assume that it's A steps. Okay, let's assume that they are A steps. So I would like to get what? I would like to get a bit from my. I would like to get a bit from my clock. So basically, let me see. I should have bit 0 equals. I have my bit 0 equals what? Equals. Let me see. Wait. Okay. Let me actually try to do this. Okay. Let's assume this one clock is not integer. Let's assume it is actually unsigned character. Okay. Let's assume that it's an unsigned character. So I would actually say unsigned character G equals, bit 0 equals clock. And then I would like to select my bit 0, so it will be 0x01. Okay, unsigned character. Bit 1 will be clock and unsigned 02. Okay. Is that okay? Let me try to have different description. Maybe that is not easy to understand. Let's put it in binary format. Is that okay? So my A equals integer B0. Let me see. My A actually is Boolean type, right? My A actually is Boolean type. So I should have a Boolean. Know what I'm doing right now? Oh no.
Not sure. Converting everything from like Boolean to
Okay, right here actually I'm writing a simulator, simple simulator. Okay, the Qt sim spin is actually written in similar program. It's actually also written in similar program like what I'm writing right now. This one actually eventually can develop into some big program like Qt spin. It's actually a simulator. Okay. So this first part is called setup. Second part is computing. Or second part can call circuit evaluation. Last part is printout. So clock I said is a simulator. Each time I step through one clock cycle, right? So now let's read the first part. The first part I have this one actually my clock starting from 0, 1, 2 to 7, right? Is that okay?
Mm-hmm.
My clock going through 1, 0 to 7, so this here no equal. Right? And then my clock should be what? Because the unsigned character, so it actually should be 0, 0, 0, 0, 0, 0, 0, 0 for the first clock cycle. Right? And then I do a AND function, so it actually is 0, 0, 0, 0, 0, 0, 0, 1. Only this guy can pass. Only this guy has a 1, it will pass.
Yes.
So effectively, this one I'm selecting bit 0. Is that okay? So effectively, this one I'm selecting bit 0. This one I'm selecting bit 1. Is that okay? Is that okay? So after I selected the bit 1, bit 2, or bit 0, if it is not a 0, I will convert it to Boolean value ABS. So I have to set up for ABS value based on bit 0, bit 1, and bit 2. That is coming from clock. Is that okay? So basically, these three variable will be what? S, B, and A, it should be what? It should be 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, something like that. You go through when your clock go from, all of them, yes. If you go through your clock one by one, it should be something like this. Right? And then each time I evaluate a circuit, how I evaluate a circuit, my S will be converted to SB. So my SB is bar of my S. My S1 is my A and the S. doing AND. So basically, I connected here to here. My S2 will be B. I connected to S bar. It will be connected like this, and eventually I have a S1 and S2 multiplexed together to create Z. So this one is a basic small 1-bit 2 to 4 1 to 2 DMAX. Is that okay? 2 to 1 multiplexing. 2 to 1 multiplexing. Is that okay?
Mm-hmm.
And then at the end, I print that out. Print out the step, how many, and then print that out. Okay, now let's actually compile. So logic simulation, let's call this guy, okay, man, save. Oh, here, it doesn't accept this, okay, it doesn't accept this. So let me see if I remove the underline. So underline is not accepted by C language. Okay, then I'm wrong. Here I seem to, when I print now, I seem to have forget to do here should be percentage S, percentage S, percentage S, and backslash N to change line. Okay, so there is the output I did not arrange correctly. And each one of them, let me push one character back. Compile. And run. You see that? So bit 0 is FFT. Let me see. I still need to have S. Let me see. I still need to have my S. So my F is not printed out. I still need to put my S over here. Okay. Okay. So first one, let me see. 0, 0, 1. Do I have my logic error? I'm sorry, this one X2 should be AND. Okay. That's 2 AND gate. I actually made a mistake over there. Let me save it. Compile and run. Okay. Okay, this time should be correct. Okay. So the first one, let me see. The circuit I'm trying to simulate is like 2 AND gate. I have A over here, B over here, right? And then here, I have this S bar for select, S for selected, right? And then I have an OR over here, right? So the first one, step 0, my A and B, both of my A and B are 0, right? Both my A and B are 0. And then my S is F, so I will select B. B will come with F value, so G is F, right? Step 1, I have T equals 1. My S is still F, I still select B, so B goes through. So when S is false, we always select B. So top 0, 1, 2, 3 all select B. So BF goes through, BF goes through, BT goes through, BT goes through. Is that okay? Is that okay, Eric?
Yeah.
And 4, 5, 6, 7, S is true, so I will select A. Select A, T will go through, F will go through, T will go through, F will go through, T will go through. So let's simulate this multiplexing.
So what happens when the clock is?
Clock plus is just, original clock is 0, then the next run I have clock equals 1.
1.
And then
So
2,
you put
3,
it
4.
under 0, 0, 0, 1, so it becomes 1.
Yeah. So clock actually, this clock actually, initially I have, say I just select 3 bit. Initially I have 0, right? And then 1, and then 2. I mean 2, and then 3, and then 4, right? So,
Yeah.
so actually I'm trying to assign this one to A, this one to B, this one to C. And this the whole thing is called clock. And my clock increase every time.
Okay.
Is that okay?
Yeah.
So basically my clock goes through the whole 3-bit format. Is that okay? Is that okay?
Yeah.
So if I have like 4 variable, say here I have D, then my clock may go through 16 different stages to have the complete B1 to B4 requirement. Is that okay? So here clock, I can actually use this one to go through all of the 2 to the power n combination. Or I can use a random number generator to select data, to generate random data and then use that data to select different bit. Is that okay? Is that okay?
Mm.
So here say if I don't do this one, and then here I select from, here I include from mass. Okay? And here actually I didn't go through my clock. So in my setup, actually I can have my integer. Let me see, unsigned integer, and I say data coming from my random int modular by 8. Okay, so this one will keep only 3 bit from random pattern, right? And here instead of using data, I use clock. So clock still will go through, say, 8 different stages. But each time I get a random integers. So let's look at the rand in C language. So what will the rand int be? Okay, let's check. Okay, so let's see, rand int. How to generate a random integer. So here I need this, and then the integer, I need to have time, and then random integer to I, right? Let me see. Random integer, let me see. I don't need a random integer, I just need a range. So this random function, let me see, okay. Random function. Okay, I have a random module, but I did not call it, okay. So here actually, rand will generate pseudo random number from 0 to rand max, right? It will generate an integer in that range. So I can actually use the, right here, I can actually do include time.h. Okay, I could include the time.h. And in front of everything, before I do any simulation, I put this in because I actually set my time to be like that. I actually set my seed using the random number generator. Okay, and then inside each simulation, I actually generate some number called rand. That is ranging from 0 to random numbers max. Okay, that's okay. I don't care about the rand max. So here, because I want to take modular by 8, it doesn't matter which it is. So I get the random integer and then I generate the R. So my R take modulo by 8. Okay, so now actually I can run and then simulate. Okay, so actually I simulate 3 steps. So here, F is false, I take B. S is true, I take B. S is true, I take A. Okay, S is F, I take B. S is true, I take A, right? S is true, I take A. S is false, I take B, right? S is false, I take B. S is true, I take A. Okay, all correct. So that's how I can set up the random simulation as well. So number one, I need a time. Time is to set the seed to be randomized. Okay, and then each time I get a random number between 0 and range, the underline max. It doesn't matter. It doesn't matter. And then actually that integer I divided by 8. No, take modulo by 8. So this random number data will be between 0 to 7, right? And then each time I get a bit for it to do simulation. And here I decouple the data from clock. So number of steps right now I can do 20 steps. Is that okay? So one is like I have a fixed pattern, and the other one is I have random pattern to do simulation for a 2 different version. But the overall simulation is to simulate a whole different bits. So same thing, your Qt spin, do that. It's like there's a big chunk of different register, different bits, and then you generate your patterns by your own fixed pattern to test the result. And it has a big for loop or while loop to help you step through one by one. So that's how the Qt spin got constructed. Is that okay? Is that okay so far?
Yes.
So this one is actually bitwise AND, OR, and bitwise complement. The next one is shift left and shift right. So let's go through this slide slow. I mean, one by one. So basically, we have this different operator, right? And the next one is bitwise operation. So basically, you have this one X, Y, each bit, OR, AND, and cap. I think this is okay, right? And then you have shift. Shift, which less length is.
Wait, what does cap do?
Cap is inclusive OR.
Oh, okay.
So if you have the last length 1, that's shift left to 1. So shift left to 1 is, for example, my original X is this, you will shift to become this.
Wait, what?
This bit will be shift. So theoretically, take one bit out. It will be 0, 1, 0, 1, right? It is shifting left by one bit. If you have this, it's shift left. This one shift right. Shift right actually will be shift right. Take the actually shift right will be, take the 0 out here. Yeah. So you become.
And then place it in the front.
Yeah, add another 0 in there and shift there. Is that okay?
Yeah. That's
a shift right and shift left. Okay, so in C, you need to be very good in doing this and also knowing the concept, so that you go to the MIPS, you can actually know what's going on. So here, 25 and 12, I have the AND operation. So this one, 0 and the 1 is got 0. 0. So the only thing we need to check is what? 0 was set, right? So you only keep those 1 actually is 1, it falls through for AND operation. Other bits are zeros. Other bits are 0. Is that okay? For AND function, just have those ones that pass through. Is that okay? Hello? Is that okay?
Yeah.
So just allow those one has 1 to pass through. Other than that, it's actually 0. So OR is different. OR, you have the ones, just check the zeros. For the ones, you just write a 1 over. So basically, these 3 ones, I just write 1. And then other things just flow through. Is that okay? Is that okay here?
Yes.
For inclusive OR, when you have the 1, those ones are actually toggle. 0 to 1, 1 to 0. And for zeros, it pass through. So here, this one toggle on this one, toggle on these two. These two and this one, toggle. Is that okay? Bit 0, bit 4, bit 5, bit 0, bit 3, bit 4, they toggle. Other than that, it's fall through. Is that okay? So this one toggle on this one, toggle on this one, toggle on this one. Is that okay? The 3 ones toggle. Other things just fall through. Is that okay?
Uh-huh.
So the next one is BY complement. It's just a big flip. Okay, this one's easy. I don't need that. Okay. Then shift. Okay. Less than is shift. So here, shift 1 bit. 1 bit that is, shift 1 bit to the left. You actually have what? You have, let me see, in binary, shift left by 1 bit. In binary, you add a 0 over there, right? You shift 1 bit, and the last bit actually is overflow. But actually, because it's like integer, so it's still there. Is that okay? And then shift 0 bit is the same. It's the same. Shift 4 bit, you will add 40 at the end. So shift function also equals to what? Shift left 1 equal to times 2 to the power 1. Is that okay? Hello?
Yes.
Is that okay for this one?
Yeah. Yeah.
Equals times 2 to the power 1. Okay. And then shift right equals divided by 2. N bit, this one divided by 2 bits. 7 bit divided by 7 bit. Right? 8 bit, it becomes 0. Is that okay? So these are arithmetic shift. Arithmetic shift means division or multiplication by 2 to the power something. Okay, and then the last one is called logical shift. Logical shift, you cannot actually, is different, defined differently, but so logical shift still be shifting, but when you shift right, say, when you actually say shift 4 bit to the left, say this one shift 4 bit to the left, this one shift 4 bit to the left, it becomes this, right? Because of the first this one, right?
Uh-huh.
And when you shift back, you actually lose some bits. You lose some bits.
Becomes 0.
Yeah, and it's not like the division. It's not like division. So this one, the arithmetic shift is exactly arithmetic shift is exactly like the logical shift, except that instead of padding zeros, it pad with the most significant bit. What does that mean? The arithmetic shift, this one,
Uh-huh.
you will pad with MSB. And then this one, just 0. Okay, that's the difference. That happens when you have the -1. Say my -1 in 2's complement, say here, -1 is like this. This is -1, right? Because original your 1 is this.
Mhm.
Right? Inverse is 1, 1, 1, 1, 1, 0, and then it becomes like this, right? So when this guy say, I'm sorry, -1 is not good example. Let me clear it. Say I have a -0, 0, 0, 0, 0, 1, 0, 0, 0. Okay, this one's -8, right? So this one's 8. And -8 should be 0, 0, I'm sorry, 1, 1, 1, 1, 0, 1, 1, 1. Plus 1, it would be 1, 1, 1, 1, 1, 0, 0, 0. So this one actually is the -8, right? So if I do right shift by 2, it will be 1, 0, 0, 1, 1, 1, 1, 1, 1. So the left side, you pad 2 bit in, but it actually is padding by sign bit 1, padding by the so-called most significant bit, MSB. So this one effectively it is the same like divided by 2, so you get minus 2. So it's like minus 8 divided by 2 to the power 2. You get minus 2. So you actually pad 1 in there. When you do this is arithmetical shift. No more shift. No more shift. No more shift. No more 2 arrow. That's arithmetic shift. Logic shift you use a 3. Logic shift you use a 3. So basically, if you have 0, 0, 0, 0, 1, 0, 0, 0, right? Your 2's complement is 1, 1, 1, 1, 1, 1, 1, 0, 0, 0. This one is minus 8, right? And then you do logical shift. So say you shift by 3 bit. What will happen is like take 3 bit out, and you pass 3 0 in front.
Okay.
So logical shift is unsigned shift, right? It will pad with 0.
But doesn't the
Arithmetic shift is padded by your sign bit. Is that okay?
By what sign bit?
Sign bit is like if you have this, right? I shift by 1 bit, you become 1, 0, 0, 1, 1, 1, 1. Here I pad with 1 instead of 0. But if I do this, it will be 0.
1, 1, 1, 1, 1, 0, 0.
Yeah.
Okay.
So the difference is here. So this is called logic shift. This is called arithmetic shift. The top one is arithmetic shift, bottom one is logical shift. Is that okay? Is that okay for this?
Yes.
Okay. And then next thing is like this one is the C part, okay? The rest of them I don't want to cover. The next one is like you need to actually study this program, right? You need to study this program well. Now, actually, let me see. Are you still all right or no?
Yeah, I'm good.
Okay, let's actually go over it, okay? Let's still go over it. If you are tired or something, you don't want to continue, let me know, okay? So this one actually is the bit level operation, so let me save. Okay, the C part, I introduced it. So right here, we actually cover the so-called bit level operations, right? And then we cover what would be passed, what will not be passed, right? So here, let's pick the last time's talk. We have this one. You remember this one? You remember this one?
Inverted OR?
The SRH.
I remember SR last, but I don't
Set
remember.
and then reset, right? And the Q over here. You remember that one? Q bar over here. You remember this one? Let's study this, okay? Let's study this. So basically, if this guy is a 0 over here,
Okay.
0 over here, right?
Yes.
0, what will happen to all gate? The data will go through. The data will just
inverted,
go through.
right?
Yeah, so when there's 0, 0, it actually is an inverter couple structure. So my data Q will be locked here, right? Is that okay? My Q bar will be locked here. So my Q here is 1, here will be 1, here will be 0, 0 will be here, and is that okay? I'll lock data.
Wait, so there's 0 from S, 0 from R.
No, so this one actually no effect.
Wait, what's the second part of the OR?
This one is 0, right?
Hmm?
But because of for all gate, anything 0, this X will pass. So that actually S has no effect, R has no effect.
Okay, so it depends on Q.
Depend on Q, yes.
Okay.
Okay, so now if here I set this one to be 1, 1 is setting, right? So if this signal is stronger, I will set this one to 0 because here is an inverter, right? This one will definitely set this one to 0. So this one will be 0 here, inverter here will be 1. So this one, if here is a 1 over here, I pretty much will set my output Q to 1 because of the inverter structure. Is that okay? Is that okay? So that's why S is a setting signal. So S and R both are 0. You actually will just keep the data. S equals 1, you will set Q to 1. And otherwise, if you have the other one, say, this time if my R is 1, my R is 1, I pretty much will set my Q to be 0, Q to be 0, and then my Q bar will become 1. So because Q is set to 0, so my R will set my Q to be 0. That is a reset or clear function. So that's why when SR both are 0, it actually keeps the data. When S equals 1, you set. When you know what I'm saying? Is that okay?
Yeah.
So then the next one it actually play is like last time we have this SR latch, right? Q and Q bar right here, right? So before our data go SO, actually the data come in, we have another one called here is actually AND gate, right? I'm sorry. What's that? Let me bring up the page. I'm sorry. Let me bring up the text, your textbook. Okay, go back to the previous memory part. Okay, this is SR latch. The next one is actually called D latch. So D latch, the original SNR are in here, SNR, right? So now this let's say S old, okay? So this new S and SO, the relationship is like I qualify with the clock. So when clock equals 0, then my SO will be 0, so no change, right? When my clock is 1, then depends on the S. SO will be S. So when S is 1, I will set. S is 0, I will not set. Is that okay?
Yeah.
So this clock is used to qualify. This one is to qualify. So there's another use for AND gate is like use clock to do qualification. So what that means? That means like my S over here is timed by clock. So basically, if my clock is 1, during this period, your S will pass.
Huh?
Your S will pass. No matter 0 or 1, you pass. And outside that period is all zeros. The S, this one is S output, S out, S0. So S0 is on this point. S0 is on this point. So my S0 outside of the clock, when clock is 1, my data is valid, will be going through, set or reset, right? And if my clock is off, basically my SR is just 0. It won't change the data at all. So that means my S signal generated by SR. So my SR now actually is valid as only when CK is 1. When clock is 1, you actually can do set or reset. If when clock is 0, you have no set or reset signal. Is that okay?
Uh-huh.
So now, if we connect the S and S bar together, that become our D latch.
Huh.
That become our D latch. Okay, so basically, this D latch is like my data qualified by my clock. Okay, so my data will go through to set data only when clock is on. So basically, it's just like this. Just like I have a latch like this. My clock is on, my data goes through. Right? Otherwise, what? My original queue will stay. Right? Otherwise, if the clock is off, actually this one is just like disconnected. This one's just like disconnected. If my clock is low, it's just like my D cannot go through. It's just like disconnected. This my Q level will stay. So this one, whatever D34 here is similar to this. Is that okay? Similar, but not the same. Similar means this one actually has the SR latch coupled, so it will keep the data valid. But the one I shown, over the time, the electronics will leak. This one actually, eventually this queue will dissipate, will go down. But the one we do has the memory. It has a close coupled structure, so it will stay. This is called D latch. Is that okay?
Yeah.
And then the next one, this one is to play trick on D latch on the clock. So originally my clock is actually a long clock. So the whole period will be one on, one off. So the whole period of time, my data will flow through. So this is called edge trigger, level trigger. So level trigger, once my clock is on, everything will go through. My data will go through to set. Otherwise, I will keep my original queue. Right? This is called D latch, the previous D latch. This one is called edge triggered. So when edge triggered, what would be the edge trigger? Edge trigger is like my clock's original this. I use my delay, okay? My delay, so my delay signal, delay clock will be slightly off like this. Okay, it's something like this. It's an inverted signal, but it actually has a delay, gate delay over there because of my inverter. So two signals end together. My CK and my CK bar D delay the CK bar. Two end together will become this.
Huh.
So what? It's become a show pass. But because of it is a show pass, so only this time the data will go through. So it's just like my clock rising, I'll catch the data on the rising edge. Just like that. If the gate delay is too short enough. If the gate delay is not long enough, what can I do? Say if this gate delay is too short, what can I do? How can I make the delay longer? How can I make the delay longer? It's easy. Actually, original is 1 gate delay at A3.
To delay it even more.
Yeah, delay even more, because these two logically will cancel out. So original is 1 gate delay, is like my signal is like this. My delayed inverted signal is like this, right? So now I actually make my delay signal to be longer. You know what I'm saying? But these two will cancel out, and then I'll get a longer edge. Well, so actually it depends on what you want to achieve, how many nanoseconds you will achieve on the rising edge. You know what I'm saying? So this one actually in the chart over here, it say that your C is your clock signal, your B is your inverted clock signal, but with some delay, and two end together, you create a little edge. Is that okay? That's your rising age time. That's your rising age time. So this become a D flip-flop with age trigger. And the previous one is called level trigger. Level trigger actually, the whole period of time, the clock will allow the data to go through. Is that okay? That's called the SR latch. Okay, and here has 4 type of data: D latch with bar that add an inverter to clock, or D latch rising edge, D latch falling edge. Okay, that's inverter to clock. That will give you the different level. And here actually this one memory. Remember that here actually today I teach the decoder again. So basically this part is to decode the two edges for you, right? This one is to decode the 2 edges for you. So each one of the data word 0 will qualify by the edges. So edges is 1. When edges pin is 1, your D will go through. If select the edges is not select, you will not go through. Is that okay?
Yeah.
So this one becomes like 4 to 3 selector, right? I have 4 edges. Each time I'll select, but 3 bit will flow out. Is that okay? 3 bit will flow out. Is that okay? So this is a 4 times 3 memory. Okay, then you can study this better. Okay. The next thing I would like to talk about is the JK flip-flop. JK flip-flop and SR flip-flop a little bit different. JK and is a little different. JK using this structure. Okay, using this structure, NOR at the end. And the end qualify with a JK and clock. Okay, and that will be complicated. So only thing that I want you to know about for JK is this table. Okay. So basically, at the rising age, you're let's look at the logic. Okay. If JK are both 0, JK are both 0, it like SR, no change. Right? If J is 1, it will be set just like S. K, it will be reset just like your R. Right? And originally S equals 1, R equals 1, what will happen? Fighting. See who comes first to tackle the data, or stronger. Right?
Okay.
But JK definition is that you will toggle. So you will get Q bar. Q will become Q bar. Q bar become Q. Is that okay?
Yeah.
So the only thing you need to remember that JK flip-flop may be tested, maybe not. But the only thing is that you need to remember this next stage data is defined by this. If your J is 1, K is 0, then you will get Q. You will set. J equals 0, K equals 1, you will reset. Both J and K are 0, no change, keep the data. And then if both of them are on, you actually toggle. Okay? So that's what JK flip-flop is. Whether you test it, I don't know, but you know it's the only difference is that when both J and K are 1. J equivalent to S, K equivalent. So you can say K is kill and J is Jacob, right? Jacob like set. Is that okay? And kill means reset, clean. But JK has the toggling feature, but SR no toggling feature. Is that okay? And ship register is do shifting. Let me see. JK, we finish that. Master slave right here. Don't talk about it, master. So let's stop here, okay?